Hi, I want to focus briefly on equilibrium expressions, how they're used in calculations and why they're important. Chapter 10 covers two topics that a lot of books might treat as separate chapters. So the first part of that is kinetics, how fast a reaction goes, and the second part is equilibrium. Equilibrium is a lot more important for us in terms of problem solving and just applications in chemistry and medicine and everything else. The first part, the kinetics, though, might be of interest, especially in the context of all the stuff going on with the COVID virus, but I'll leave that for another day. So on page 363, there's a description or discussion of equilibrium expressions, and to kind of summarize what's here, for a generic reaction, and chemists like to say AAs plus BBs goes to CCs and DDs, just to have it just as an arbitrary general reaction. And we can take that reaction and from it write an equilibrium expression, which is concentration of products over concentration of reactants. More specifically, it's the concentration of each product raised to the coefficient in the balanced chemical reaction. So it's products over reactants, but there's a little more to it than that. The other thing that's important to keep in mind is things that don't change concentration. So pure liquids or solids don't show up in the expression. Only things that have meaningful concentrations. So if we look at a specific example where we have one hydrogen plus one iodine gives us two HIs, we write the equilibrium expression as products over reactants. So my HI concentration is over the H2 and the I2, and the coefficients, that stoichiometry that's in the balanced reaction, shows up as exponents. So we have the HI, which we had two of, results in HI concentration being squared, and the H2 and I2 are raised to the first power, which of course we don't show. Where we want to go with this is we need to be able to take a balanced reaction, write an equilibrium expression, and then solve that equilibrium expression for any part of it. The overwhelming majority of problems, you will be given all but one piece of information. So maybe we're given the HI concentration, the H2 concentration, and the I2 concentration, and then you have to calculate Kc, so just plugging in numbers. Other times, maybe we'd be given the Kc, the HI, and the H2, and have to solve for I2. So in that case, we'd have to rearrange this to come up with an expression that says concentration I2 equals whatever it equals, and then plug things in. In that case, it would just be that I2 equals HI squared over H2 times Kc. But again, that's straight math. There's no fancy chemistry rules there. Okay, so here's a typical problem. We're given a balanced reaction, or maybe we're given a reaction that's not balanced and we have to balance it. Then we're being asked what the value of K is at a given temperature. The temperature is not used in the calculation, but it changes, that is, K changes with temperature. So if they want us to calculate the K, we really should be specific about the temperature. If we were to calculate K at 200 degrees, but this concentration information was at 100, we wouldn't be able to do it with the information available. All right, so back to what I said a minute ago. Once we've got this balanced reaction, we have to be able to write the equilibrium expression. And again, that's products over reactants. So our NO2 is the product, that's in the numerator, and the N2O4 is in the denominator. And because there's a 2 here in the balanced reaction, we have the squared term in the equilibrium expression. All right, they've given us all the information about concentration, so we just solve for the Kc, it's already solved for. Oops, there we are. Solve for the Kc, it's already solved for. Plug in the numeric values and come up with an answer. Generally, we don't bother putting units on the K. It's understood how it's calculated, and we just sometimes have to be picky about whether it's something called Kc or Kp, but again, beyond the scope of what we care about here. Question 60 in chapter 10 is an awesome question. It's one of the few that isn't as simple as the rearrange the equilibrium expression and plug in the known values. We actually have to do a little bit of use of balanced reactions and stoichiometry in this. And we'll do that with something called an icebox, which I'll demonstrate in a moment. Take a good look at the question. I'm going to have this disappear and then just solve from here. The icebox technique is essential for solving anything but the most rudimentary equilibrium problems. It's also useful as just sort of a bookkeeping tool for other chemical reactions, limiting reagent stuff, or needing to find a final concentration, that sort of thing. And what the I stands for is initial change in equilibrium. So we often know what our initial concentrations of things are, and we often know what we have at the end of the reaction. And so we can use that difference, initial to equilibrium, to figure out what the change is. Sometimes we need to combine multiple equations into one, taking two equations to solve for two unknowns, etc. So again, this is what the icebox technique startup looks like, where we write down what we know and then we figure out how to solve for the missing pieces. So in the problem, they tell us that initially we have 0.6 moles of the PCl5 in a 1 liter container. So we have moles per liter, which is a concentration. So they tell us moles, they tell us it's 1 liter. We really care about concentration, which, because it's 1 liter, is the same as the number of moles. Then they tell us at equilibrium we have 0.16 moles of PCl5. So initially the only thing we had was the PCl5. So doesn't say it, but that means that there's none of the PCl3 or the Cl2. Okay, so again, what we care about is that whatever we started with a difference applied to it, tells us what our final amount is, or our equilibrium amount. So what we need to do then is say, well, what are the changes? Because I need to know, for this problem, all three of these concentrations. And right now I only know the PCl3. So what I can do is say, well, if I started with 0 and I ended with 0.16, it means I created 0.16 of the PCl3. Since the stoichiometry is 1 to 1 to 1, that also means that I created 0.16 of the PCl2, which means my equilibrium concentration there is 0.16. And if I created 0.16 of this, I must have consumed, so I'll do that with a negative number, 0.16 of the PCl5, which leads me to, it's going to be 0.44. So that's how I figure out these three concentrations. The rest of the problem has to do with calculating what K is, and so this would go to the fundamentals here, that if I have my reaction, I won't rewrite it, but that K, which is products over reactants, will be concentration PCl3 times concentration Cl2 divided by concentration PCl5. And then I plug in the numbers, so it'll be 0.16 times 0.16 over 0.44. And numerically, we can work that out. Here's a more complicated problem. If you're up for the challenge, go ahead and try to work this out. So pause the video and do it. If you're more on the lazy side, then just follow along. But what we're going to try to do is find the concentration of fluoride ion in a solution that's saturated with calcium fluoride. So the things we need to know is what's the reaction. That would be solid calcium fluoride dissolving to give us aqueous calcium ions and aqueous fluoride ions. And that's important. In the equilibrium expression, the solid will not show up, but the dissolved ions will, because they have concentrations that mean something. So the equilibrium expression would be that K is equal to the calcium ion concentration times the fluoride ion concentration squared. That equilibrium constant is actually called a solubility product, so it's written as KSP. Doesn't really matter, it's treated the same math-wise. but numerically that's 3.9 times 10 to the minus 11th. So that's typical of KSPs. They're very, very low numbers, but that's very important. That's how minerals form, that's how your teeth form, based on some of these solubility properties. All right, we do that same icebox thing where we say, well, let's figure out what goes on. And so we might say we will let X, should have done this in the other order, but let X be the equilibrium concentration of calcium ions. So initially, in my icebox thing, I'm going to have 0 of the fluoride and the calcium, and the change we're going to say is going to be that X, or we could say the equilibrium is the X, the same either case. What's important here is that for every calcium that dissolves, we get 2 fluorides, so this is 2X. Okay, so our equilibrium concentrations then are these two guys right there, and we need to substitute them into that equilibrium expression. So K is equal to my X times 2X squared, or it's equal to 4X cubed. I want to solve for X, or rather I want to solve for 2X, that'll be my fluoride ion concentration. But doing this math-wise, I would have that X cubed is equal to the value of K over 4, or X is going to be the cube root of K over 4. All that algebra you took, whenever you took algebra, is coming into use here. Okay, so numerically again, we're just going to plug that in. So we have the cube root of 3.9 times 10 to the minus 11 over 4. Depending on your calculator, we would do this 3.9 times 10 to the minus 11 divided by 4, have a quantity there, and then you can either raise that to the 1/3 power. I think my smartphone has a cube root button on it, but however you manipulate that on your calculator would be the right way. All right, so when we do that, and I get 2.1 times 10 to the minus 4. And remember, what we did here is we solved for X from that equation. My X was the concentration of calcium, my fluoride is twice that. So again, if my fluoride is what I care about, I need to be careful here and say that's 2 times X, which is going to be 4.2 times 10 to the minus 4. Actually, I think it'd be 4.3 because this was 2.14, so I rounded down a little bit close enough. All right, so just sort of perspective again. The concentration of calcium would be the X, that's 2.1 times 10 to the minus 4. The concentration of fluoride is twice that. We have a neutral solution because the calcium, of course, has a +2 charge on it. The fluoride has a -1 charge, but there's twice as many fluorides, so it all works out.